Welcome to Maths with EJD. We're still talking about spectral analysis, and in this video, our focus is on cross-spectral analysis. Cross-spectral analysis, and it's important to know that cross-spectral analysis extends the concept of spectral analysis to two time series, say X of t and Y of t. All right, so you have two separate time series analysis, and then you want to do an analysis on these two. So while the power spectrum of a single signal describes how its variance is distributed across frequencies, the cross spectrum investigates how two signals are related in the frequency domain. Okay, in fact, I can try to tidy this up by just doing this. This. Okay, so I can have this. All right. So formally, the cross-spectral density CSD between x of t and y of t is S of xy. You know, we are used to talking about S of xx. Now we have S of xy. S sub xy of f equals the limit as t tends to infinity. T, I think, is the period. I think we're going to see all of that. Of 1 over t, the expectation of xt of f multiplied by xt prime, xt star of f, that is, where xt of f and yt of f are the Fourier transforms of truncated signals, and x denotes complex conjugation, and e dot is the expectation operator, all right, like in statistics. So the CSD, the cross-spectral density, I believe in this case, is generally complex, containing both magnitude and phase information. So in addition, in line with that, we have to talk about a coherence function. So we have coherence function when we talk about cross-spectral analysis. So the coherence function quantifies the strength of the linear relationship between two signals at each frequency. It is a normalized measure ranging between 0 and 1. So, and it's given as gamma sub xy squared of f, and that is the absolute value of s sub xy of f all squared, all over sxx of f times syy of f. Okay. I think that's it's giving some idea close to covariance and things like that. So where sxx of f and syy of f are the orthospectral densities, which are the power spectra of x of t and y of t respectively, and then s sub x of xy of f is the cross spectral density between x and y. The interpretation is that you know, gamma sub xy squared of f is equal to 1. All right, that's if it is equal to 1, then we have perfect linear relationship at frequency f. Then if it is 0, then that means there's no linear relationship at frequency f. So if you take the gamma xx of f at a particular frequency, all right, and then you get 1, then it means there's perfect relationship between the two, and then if it's 0, there's no relationship. So intermediate values indicate partial coherence. So you can then have values in between like 0.5, 0.3, 0.8, and all that. So for applications now, this is really good for detecting functional connectivity in neuroscience, talking about EEG and fMRI, then identifying coupling in engineering systems, talking about vibration source to response, and signal transmission reliability in communications. So another concept you need to understand about cross-spectral analysis is the idea of phase spectrum. So the phase spectrum represents the phase shift between two signals as a function of frequency. So, since cross-spectral analysis is about two different time series signals or time series data set, if you like. So the phase spectrum represents the phase shift between these two signals as a function of frequency. So in that case, that's phi sub x of y of f is then it takes then arg s sub xy of f. So by way of interpretation, the phase spectrum provides the average time delay between x of t and y of t at each frequency. Then if phi sub xy of f is equal to 0, the signals are in phase at that frequency. It means they are perfectly together. Then a positive phase indicates that x of t leads y of t, while a negative phase means y of t leads x of t, right? So for applications, right, it's good for delay estimation in seismic and acoustic analysis. Seismology is about the earth crust, right? About earthquakes, and of course, acoustic talks about sound and all that. Understanding causal directionality in physiological systems. So you want to know causal directionality in physiology. Then phase lag in control systems and mechanical vibrations. Phase spectrum can help with that. All right. So we now have transfer function estimation. So the transfer function h of f characterizes how input x of t is transformed into output y of t in the frequency domain. So we have h of f equals s sub xy of f all over s sub xx of f, where s sub xy of f is the cross-spectral density, while s sub xx of f is the input autospectral density. All right. So when you hear it's just like autocorrelation, right? Autospectral density is about density within a single signal or a single uh, variable in a data set, so to speak. So by interpretation, the absolute value of h of f. So here you gain at frequency f. This talks about gain at frequency f, and arg h of f is phase shift introduced by the system at frequency f. So the applications include system identification in engineering, characterizing filters and transfer paths, modeling input and output dynamics in physiological and economic systems. Then we can talk about the Python implementation. First of all, we import the helpers. Talking about we do the imports and the helpers. The imports are the libraries or packages we have to import, like NumPy, Matplotlib, and SciPy. And then the helpers are the preliminary things we need to do. Like here now we do this line 5 to ensure that since we need some randomness in what we are doing, we want to be sure that whatever random thing we get is the same throughout. So that's what this seeding is about. And then we define two functions, db and deg. All right. Deb is to return 10 log 10 of the maximum x, and deg is to return 180 pi minus x or something like this. Yeah, 180 raised by minus 1 times x. Yeah, so that's what we have. So of course you have this may not give it's not giving you any result, but it's necessary for the next set of results we are looking forward to getting. All right, so that works. Then we can create input-output pair with a known LTI system. So in this case now we have the sampling frequency to be 1000. The period is 60 seconds, and n is integer t times fs, whatever it is. So we just want to take the integer part, but of course this will give us 60,000.00, but we don't need the decimal parts. We need it to be integer. Then we need t, that's a range n over fs. Then we impute colored low pass noise. We design a gentle low pass to give X some structure. So we have B underscore LP, A underscore LP. Then we get signal the butter into 4 by 60 and all this. Then X is signal dot filter BLP and all of that. Then we have the true system, which is unknown to the estimator. So it's second order resonant bandpass. F naught, that's this fundamental frequency of 20, Q is 4.0, W naught is 2 pi F naught, and BW is the W naught over Q. Then we have B underscore BP, A underscore BP, and all of that. So, I mean, you can take a closer look at this. I'll just go ahead and run it, and then it gives us something beautiful like this. So it gives us the input X of T and output Y of T like this. So, so we have so that's under the idea of input output pair like that. So we see that at some points the two signals are in phase. At some other point they are out of phase. That's the point where you see there's one shooting out separately from the other. Then we can also talk about spectral settings, say for Welch through cross spectral density and estimates now. So we have the parameters number per segment, and then the number of overlaps, which is usually the number per segment divided by 2, the whole number part. Then we use the windowing method, which is hand in this case, and we trend with constant, and then we do auto and cross spectra. So all the PXX, PIY, SX, SXY, and so on, and we do signal.welsh, and I mean, the key things that will be different to be the X, Y, and X, and whatever. Of course, this is signal.welsh, this is signal.welsh, this is signal.CSD. So all this, then you have the coherence, you have the phase spectrum, and then you do the transfer function, which we saw the other time. So I run this. We don't expect any result here. So that's just setting the ground for what we are going to get next. So we can then plot the autospectral and the cross-spectral density as defined previously. So using semiology, so we run that and then we have this. So we have the auto power spectral densities. So the blue one is for X periodogram, and the red one is for the Y periodogram, right? And then we have the cross-spectral density magnitude. We have this now. This is absolute of S sub XY. And then we can plot the coherence based on what we see, what we saw up there too. So this is what the coherence looks like, right? So we know the coherence is between 0 and 1. So for the most part, it's something very close to zero, close to 0. All right. Of course, we have a peak coherence somewhere close to 1, right? And then we can plot the phase spectrum, that's cross spectrum and transfer function phase. We run this now, and this is what that gives us. So we have cross spectral phase unwrapped, and then we have estimated transfer function, which is also unwrapped. Then we can go ahead and do the plot transfer function magnitude, both like and compared to ground truth. So of course we set the necessary things. So ground truth discrete time frequency response to the resonator unknown in real cases. So we have W and H true. That will be signal.fregs of B underscore BP, A underscore AP, A underscore BP, WRN equals length F, FS is F, and all that. So, and then we do the plotting. You can take a closer look at the code. And in this case now, the blue line talks about the absolute value of H of F, which is an estimate, and the orange line talks about the true thing, which is actually the reference. All right, so you can see that from somewhere around this frequency around here. Okay, let me see if I can reduce this to see. Okay, I mean everything that has been starting from the up. Okay, so you can see that there's a bit of alignment from 0 to say to somewhere around say 70 or 80, and after that you have a departure of the estimate from the reference point. Okay, so in fact now begins to mirror it somewhat. So instead of curving down, it curves up like that. So that's some kind of departure. Then we also have transfer function phase. So here now we have we have angle HF degrees. All right, that's the green one, the blue one, and then the orange one is the straight thing, which is the true one, actually. Okay, so from there we can talk about the coherence-based good band and delay estimates, which can be optional. All right, so you can choose frequencies where coherence is high and trustworthy for TF estimation. So we have THR is 0.6. Then you have CHXY. So you have all of this. I mean, you can take a closer look if you're interested in that. So peak coherence is at minus. So from this, we can read that peak coherence is approximately 20.02 hertz with gamma squared approximately 0.945. So estimated broadband delay is tau, which is approximately 32.16 microsecond, where coherence is greater than 0.6. Of course, all of that is coming from the code here. So you can try to understand the code. Then notes on method choices. So Welch slash cross-spectral density settings, number per segment, overlap and window, control the bias variance trade-off, coherence confidence. For K average segment, degree of freedom is approximately 2K, higher K tightens variance. Then we have the cap H of F, which is SXY over SXX, is the non-parametric TF estimate and reliable where coherence is high. So you have phase unwrapping which prevents artificial plus or minus pi jumps, and delay from phase slope is most stable in bands with high coherence and smooth phase. So what can we tweak from that code, from all the codes you have seen? You can increase T, the period, and change the number per segment to adjust the window to trade resolution versus variance. You can change the system. You can change the true system with IRP, Butter, Chevy 1, etc. to demonstrate different dynamics. You can raise or lower output noise to show how coherence degrades TF estimation. So optionally, you can add a confidence interval overlay for coherence, which is approximate, and a non-parametric impulse response, which estimates via inverse FFT of H cap of F. In summary, we see that cross-spectral analysis generalizes spectral methods to two signals. So instead of doing spectral analysis on just one signal, you can do it for two signals. Then we can also have it's just like, so if you want to think about it in terms of statistics, right? Spectral analysis is like autocorrelation, while cross-spectral analysis is like is no, spectral analysis is like autocorrelation, while cross-spectral analysis is like correlation between two signals. All right. So coherence function quantifies frequency specific correlation strength, and this we have the formula right here. Like that. Then for the phase spectrum, it measures time delay stroke lead relationships across frequencies. We have the formula defined like this. Then we have the transfer function estimate, which models input-output relationships in the frequency domain, and it is given as h of f equals s sub x y of f all over s sub x x of f. Together, these tools provide, I mean, all the cost as coherence function, space spectrum, transfer function estimation, and cross-spectral analysis. Together, these tools provide a powerful framework for analyzing how two processes are dynamically related. By two processes, we're talking about two signals, two data sets, and all that. Uh, how they are, I mean, two time series, how they're dynamically related across different frequency components. So with this, we come to the end of this very interesting video. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. If you have subscribed already, thank you so much. If you haven't subscribed, please go ahead and subscribe. Don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then you can take it a step further. You can become a member of the channel, and that comes to some very special privileges. Click on join, and you find those levels of privilege, and feel free to join as a member of the channel. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.